to Minnesota for about 22 years, and I guess the winters there finally got to him, so he decided to go south. And south, in his case, was the University of Tasmania, and there he's been the head of various schools. And I noticed that in 2018 he says he's now just a professor and free at last. Many of you probably have used some of his work. There's a well-known paper, Dickey and Lockman for NH, Dickey and X-ray, and he's the one responsible for that, so you can blame him or praise him, depending on how you feel. And so I'll, no further ado, we'll let John talk to you about H1.
Thank you, Mike. So I moved to Tasmania for the sake of the Magellanic Clouds, and that's what I want to talk about today. And let's see here. So yeah, thanks very much for coming, and thanks very much to Mike and to Saku Vertilik for inviting me here. We finally are making some progress on a very long-standing collaboration that we've had going for quite a while, and I've taken advantage of the opportunity to learn a little bit about high-energy astrophysics. When Mike said you can give an HEAD lunchtime talk, I said, oh great, I'd like to talk about H1 and the Magellanic Clouds. And Saku said, well, it's a high-energy astrophysics talk, so why don't you talk about high-energy astrophysics? So I had to think about that for a while, and I must say I've been doing a lot of reading for the last few weeks, but I'm still going to talk about H1 and the Magellanic Clouds, but I will get to some questions that I think only high-energy astrophysics will be able to answer. And those will be in my last few slides. Let me remind you of the very basics about H1, atomic hydrogen in the Magellanic Clouds. The H1 masses are both about, for the LMC and SMC, about 4 times 10 to the 8 solar masses. And that depends a bit on where you draw the line. But there's a fairly sharp drop in the surface brightness of the 21 centimeter emission. So you can sort of tell where the galaxy's edges are in H1. But there's an awful lot more H1 around and between the Magellanic Clouds and reaching out into the Magellanic Stream. So more actually than in either of the clouds by themselves. And if you add it all up together, you get about 1.3 times 10 to the 9 solar masses of H1, which isn't all that different from the disk of the Milky Way, which is probably between 3 and 4 times 10 to the 9 solar masses. The gravitational masses of the two clouds are very, very different. And we learned that also from the H1 by fitting rotation curves. I must say people have hesitated to fit rotation curves to the SMC, including myself, because it's very difficult to tell what the inclination is, and it's also pretty difficult to tell where the kinematic center is. But anyway, Enrico De Gioro has a nice paper which is now accepted where he develops, I think, a very comprehensive gravitational potential model, which gives about 2.4 times 10 to the 9 solar masses for the SMC. The SMC is a true dwarf galaxy. The LMC is not. The LMC is a Magellanic irregular, but with a mass of a couple times 10 to the 10 solar masses. Now, these are obviously my opinions, but what I'd like to do is take you back in time a little bit and run very quickly through the last 60 or 75 years. Most of the numbers on my last slide, in fact, all except the SMC gravitational mass, were derived very accurately from this telescope on the right. Kerr, Hinman, and Robinson, 1954, was the first map of H1 in the Magellanic Clouds. And that's not Kerr, Hinman, and Robinson over there. That's Ruby Payne Scott, Alec Little, and Wilbur Christensen. They called him Chris Christensen. It looks like Christensen's looking at his phone, but I assure you, we didn't have mobile phones in Australia in the 40s. It's interesting that Ruby Payne Scott and Alec Little look like they're having the time of their lives. So they were setting up the Potts Hill Field Station, which was the first dedicated radio observatory in Australia. And if you've read Miller Goss's biography of Ruby Payne Scott, you'll know that she suffered from terrible discrimination and gender prejudice later from CSIRO later in her career, which was a tragedy. But at least at this stage, she obviously was contributing a lot and enjoying it. Anyway, this is the map of the LMC on the left and the SMC on the right, made with that telescope. And after another decade or two, along came Parkes. This is how Parkes looked when it was first finished. Now there are stately trees all around and comfortable buildings and so on. But this was Parkes in the 60s. This is probably the most comprehensive map of the Magellanic system made with Parkes. from Mathewson and Ford in 1984. The SMC, which is down here on the right, was actually, that data was taken from Hindman 1967, and this is Hindman's Parks map of the H1 and the SMC. We talk sometimes about a bar in the SMC and a wing that goes off to the left there. But most of the star formation is either here or, going back in time, works its way back along the bar. Now, there wasn't much improvement for several decades until the compact array became available. But using the compact array on H1 in the Magellanic Clouds is tricky because you have to fill in the short spacings, the short baselines, using the single dish map. And so that took a lot of work. And if I now go from the Hindman map to the Stanimirovic map, which is a combination of the short baselines from Parkes and the longer baselines or the higher resolution from the compact array, it was quite an improvement. Here's, if you don't do that correctly, on the left is just the compact array map. On the right, the compact array plus Parkes map. You see it makes a huge, huge difference. Now, finally, moving to the most recent epoch, which began, well, nominally it will begin in February of next year, but we have some data that I can show you already from the Australian Square Kilometre Array Pathfinder, or ASCAP telescope. ASCAP is 36 12-meter dishes. You can't see all 36 here, but they're all done. And they're almost all fitted with their phased array feeds. If you see the little green circle in the middle at the prime focus, that is a phased array feed. And the CSIRO has become, I think, the world leader in building phased array feeds. The green kind on the left were designed, and the first 6 were made in 2011. They put them on 6 of the telescopes and played around for several years and decided that they had to do better. So the second on the right is the so-called Mark II, and this is what they've now built 36 of, and they're all delivered on site, and I think at least 30, maybe 32 or 3 antennas have been had them mounted in prime focus. So we can run now with 30 antennas, but the data I will show you was taken with just 16 antennas. And so this is a color representation of the map of the SMC made with a combination of the compact array plus Parkes. And I'll now just change that over to the map made by McClure-Griffiths et al. Using the 16 antennas of the ASCAP, Australia Square Kilometre Array Pathfinder. Quite an improvement. On the left is the older one, on the right is the new one, and you can see the numbers. But what it all comes out to is that the phased array feed gives you a gain or an advantage in mapping speed of about a factor of 200 compared to having individual dishes with single point feeds. And that was the whole idea, and I think it has paid off really well. That is, all these numbers have now actually been measured in the map that we made. It's funny, you don't see that much of an improvement, from there to there. But what you may notice is that with the much higher angular resolution, the things which are just sort of smudges in the H1 in the older map now resolve out into quite detailed fine structure, which doesn't look at all like a smudge anymore. I mean, it could have stayed looking like a smudge, right? But it doesn't. What it looks like is quite extraordinary features. Now, this is a zoom in on the spectral line cube. And each of these maps contains 3 or 4 channels from the cube at different velocities. And what's white here has about equal amount of emission in those 4 channels. The channels are colored red, green, blue. So what looks colorful is narrowband emission, which is not the same over that whole range of velocities. And as it works out, what's white here is essentially gas that's in stable circular orbits with the rotation curve velocity that corresponds to its position. So that is to say, it is in gravitational stability with the gravitational potential. On the other hand, the things in colors are not. And you can see there's quite a few of these little things that appear to look a little funny. Here's a movie of the other end of the cloud from the one I just showed you. And if we step through the channels, you'll see that the white gas is most of the gas, but you'll start to see some flashes of color around the edges. And those flashes of color correspond to gas which is far from gravitational equilibrium in the potential. And you'll also see that it's funny looking. It's not just a smudge. Naomi McClure-Griffiths has analyzed this pretty carefully, and it's funny, it really points the finger, that is, not only in the two spatial dimensions which we map, but in the velocity dimension. You can very clearly define velocity gradients and axes of these structures that all seem to point to where I pointed you on the sort of main bar of the SMC, where star formation, not where it is most intense today, but where by looking at stellar populations, we can see the star formation was quite intense sort of 50 million years ago or so. And that's indirect evidence that maybe this gas came from there. If you look at these structures, well, what's most interesting is that they're long and thin. They're marginally resolved in the narrow direction, that is 10 to 20 parsecs, but several hundreds of parsecs long. Their masses are sort of a few times 10 to the 4 up to a couple of million solar masses of H1. Their line widths are quite narrow. That's why the colors are so dramatic, because they have quite narrow velocity width. And that indicates, although we don't have the resolution we want to have, but it indicates temperatures in the cool neutral medium zone of 100, 200 probably in kelvins. Their velocity deviation from the stable circular orbit velocity at that position is on the order of sort of 50 kilometers a second. And that suggests that much of this gas is not going to stay in the SMC. If you look at the velocity distribution function, so positive velocities, positive velocities on the right, negative velocities, which would be towards the Milky Way on the left. There's a long tail in the velocity distribution function of the H1 mass, which corresponds to quite a bit of it escaping. We don't know exactly the escape velocity, but I think somewhere in this range, most of that gas will escape. And it's from that Naomi derives this number of 0.2 to 1 solar mass per year of mass loss in hydrogen from the things that we're looking at. Now remember, I said there was just 4 times 10 to the 8 solar masses of hydrogen in the SMC. So at 1 solar mass per year, that means the SMC will empty itself of hydrogen on the order of 400 million years. 400, 500, maybe a billion years, but it's quite rapid, and in fact, it roughly equals the star formation rate in the SMC, its mass loss rate. Where does that gas go? That gas almost certainly goes into the Magellanic Stream. So here are a couple of images of the Magellanic Stream, which I hadn't showed you before, and these sort of mark out where fairly clear discrete clouds in the H1 are in the stream. Now, we're working our way towards the high energy now. The stream, well, the Magellanic Clouds, this is a funny plot because the galactic center is at the edge. The Magellanic Clouds are here. The Magellanic Stream reaches all the way over to here in the image that I showed you last time. But notice that it sort of fits in with a lot of other high velocity H1 gas that halfway at least covers the sky. Most of the rest of that high velocity gas we think is much closer. We think it comes from the galactic fountain. And in some cases, distances have actually been measured of a few kiloparsecs out to about 10 kiloparsecs. The circles here are O6 detections in absorption from fuse. And the colors of the circles correspond to this velocity scale, which is coloring in the H1 high velocity. And so I think there is a lot of high velocity H1 which is in the halo and which has corresponding hot gas. And by the way, it has corresponding warm gas too, lots of H alpha, lots of carbon-4, and so on. So now we come to the questions for high energy astrophysics. And I just put in the background this beautiful observation from the SDO, the Solar Dynamics Observatory. And you can just watch that trickle down as I talk about the rest of this. Will the Magellanic Stream and the H1 being ejected today from the SMC eventually just evaporate, heat up, and join the galactic halo? Or let's call it the corona. The galactic halo is a gravitational structure the corona is the hot gas that fills it? Maybe. If so, what will heat it? What will ionize it? How long does it take, and where does the gas end up? And we have that problem, those problems for all of the halo, or the coronal gas in the Milky Way, since after all, the second law says you can't carry heat from a cooler object to a warmer object, and the temperature of the coronal gas is on the order of 10 to the 6 degrees. Anyway, if not, if all of the Magellanic Stream and all of this H1 which is being lost from the SMC does not end up as just hot gas in the halo, then what is the gain factor? And by the gain factor, I mean there's mass lost from the Magellanic Clouds. That's a negative dm dt. That times some gain factor, times -1, is what's gained by the Milky Way disk. If the gain factor is 0, that means you'd answer yes to the top question. If the gain factor is 1, that means all the mass, the H1 mass lost from the SMC, will eventually make its way to the disk. But G could be bigger than 1 as well. What would make G bigger than 1? Well, remember, I mean, in the background you see an example of this. The corona is thermally unstable. The galactic corona is thermally unstable. A density increase can lead to runaway cooling. I left out the word cooling, sorry, as in coronal rain. The Magellanic Clouds are moving supersonically through the coronal gas. They're moving at about 400 kilometers a second. So that can start a so-called shock cascade, a series of shocks which each time bounces the density of the gas up. The stream does show a turbulent boundary layer. I haven't shown you the evidence for that, but people have studied that in some detail, mostly with far UV absorption. Cooling times are long in the outer halo, that is beyond about 100 kiloparsecs from the disk. Cooling times get up to about the Hubble time. But in the inner halo, and by that I mean closer than the Magellanic Clouds, which are at about 55 kiloparsecs, the cooling time is as short as the orbital time or less. The orbital time is about 1.5 billion years for the Magellanic Clouds. It's not clear that they've done any orbits like that. They may have recently come into the Milky Way's gravity, but that would be what the orbital time would be. And finally, the galactic fountain is constantly sweeping out the gas in the lower halo. Out to about 10 kiloparsecs, there's constant mass flux in and out. And that means that you can't have a hydrostatic equilibrium atmosphere reaching all the way down to the disk. So, and here's really the question for you, why don't we see a Milky Way cooling flow in the X-rays, as we see in some clusters of galaxies, as we may see in some early type galaxies? And I guess my question is, maybe we do see that. Maybe we do see that, or we just sort of haven't been able to look the way we need to look. We do see far UV absorption line diagnostics that show there is plenty of hot gas, oxygen 6, 7, and 8. Much of it is in the same places where we see the H1 in the halo, particularly around the Magellanic Stream. Most of the hot gas detections, well, I just said that, near the stream. So the question is, can we map the density field of the hot gas in the halo? It's one thing to say, well, a hydrostatic equilibrium would have a certain density profile. But the question is, how much is that density profile modulated from point to point? Because since the cooling goes as n squared, it doesn't take too much modulation to start runaway cooling. And finally, can we directly see the cooling lines in emission? Because that's what, when we began to see the fine structure lines in the interstellar medium, then suddenly we could be very quantitative about the heating and cooling balance. Now, I don't think, I'm no expert, but I don't think we have yet seen the lines that are important for the cooling of the Milky Way corona. But if we could see them, I think that would really be very helpful for understanding its physics. So my conclusion, oh yeah, and let me say, I've been reading about ARCUS, which I guess is a project led from here, and that maybe could give a lot of answers, but I don't understand if it can actually see the cooling lines in emission, maybe only in absorption. So quickly, my conclusions. Improving the resolution and sensitivity in 21 centimeter emission brings new astrophysical understanding of the relationship between star formation and outflow. Tracing the gas dynamics will show how the interaction between the Milky Way corona and the Magellanic Clouds is changing the evolution of all three galaxies. And we do need to measure the G factor directly. And now let me just run you through these many decades of research and struggle with telescopes one more time. And here's where we stand today. We hope to do much, much more next year in terms of ASCAP surveying. But if you want to see the Magellanic Clouds with your own eyes, the place to come is to Tasmania, because you can come at any time of the year. They're circumpolar for us. Thank you very much.
Questions for John?
So, what about the millimeter and submillimeter wave cooling lines? I mean, it would be interesting to see atomic carbon.
Yes, people like you have done that, yes.
Well,
Yes.
I've not in the stream. And
Not in the stream, no. That's pretty hard to see in the stream. It would be very interesting to know the thermal balance of the neutral hydrogen around the Magellanic Clouds, in the stream, in the bridge, etc. I think from the South Pole Telescope, you and Tom Bania did about as much as we can easily do. Now, there are proposals to ALMA to go deeper on not C1 and not C2, but on CO and some of the other tracers.
Well, there's a balloon project, Gusto.
Yeah.
That will do a lot of this.
I've heard of that, yes. On the other hand, what I'm mostly talking about is much hotter, right? I mean, that's from 10,000 degrees to 1,000,000 degrees, and there, unfortunately, those far IR lines won't help.
I'm very pleased that rain has come up again, because I wrote about rain in quasars, and Mark Boyton and McDonough have written about rain in cooling flows. It seems to be a trend.
Well, you know, we've known the shape of the cooling function since the 60s, and we've known the condition for stability, which is a certain slope, and we know that there's hardly any place above about 10,000 degrees, well, 20, 30,000 degrees possibly, where you can have heating-cooling balance. I mean, that's maybe an overstatement, but yeah, I mean, you can easily get thermal runaway cooling. Good, thank you.
No more questions? Let's thank them again. Our next speaker is Chadayammuri. She's a pre-doc student. And she's working on simulations of AGN feedback in galaxy clusters. She's worked on, she actually comes to us from Yale University, where she previously worked on dark matter substructure. And she actually got her bachelor's at Brown University, where she was doing some more observational work, looking for faint dwarf galaxies in SDSS. So today she's going to be telling us about some of the work that she's doing here on AGN feedback.
Does this work? Yeah. So just a quick correction. I will be talking about work that I'm finishing up from Yale. But it'll sort of flow a little bit into what I'm doing here. Hi, everyone. So my name is Urmila Chadayammuri. Everybody calls me Mila. You can do that too. What I'm going to talk about today is what we can learn about the formation of non-cool cores in galaxy clusters, and what is the intuition that we can gain into really the details of this mechanism using the Romulus C cosmological simulation. So for a bit of background, as Mark just mentioned, Mark Voigt, Megan Donahue, and a lot of other people, and Grant, for example, have done a lot of excellent work recently on understanding the multi-phase nature of the intracluster medium, so the gas between galaxies in galaxy clusters. A few years ago, their team essentially noticed that if you look at the accept sample of galaxy clusters, you can sort of divide them into two categories, those with and without multi-phase gas, right? And once you look at the galaxy clusters with a fair amount of cold gas, then you observe entropy profiles that are declining pretty much all the way towards the cores. And these are what you call the cool core clusters. On the other hand, when you look at the clusters without multiphase gas, the entropy profile instead flattens out in the central regions. And there's sort of this, this dichotomy between these two populations. And to first order, right, the non-cool cores are essentially consistent with a simple model where you essentially don't have any cooling happening in the core. Of course, that's physically not what happens. There has to be some sort of interplay between heating and cooling processes that would result to things looking this way. But this is sort of the basic picture that came about. Why would you want to understand this dichotomy? Well, if you have two clusters of the same mass, but one of them has a cool core and the other one has a non-cool core, the cool core is going to be denser in the center, right? The X-ray luminosity is going to go as the square of the density. So a cool core cluster for the same mass is going to be brighter than the non-cool core cluster. So for sort of cosmological motivations, which I tend to be biased towards, bad choice of words because it introduces a bias, right? So if you really want to understand the distribution of cool and non-cool cores in your sample, if you want to go from, say, an X-ray luminosity survey to any sort of mass function that you could use for cosmology. On the other hand, you also want to understand this just for astrophysical reasons, right? So you want to figure out how in galaxy clusters we manage to avoid these runaway cooling flows that would be predicted by just simple models of cooling, if you know the cooling curve. And this also plays into forming realistic galaxy populations, because otherwise you would just have these excessive star formation rates and lots of cold gas in the centers of galaxies and galaxy clusters. And so by trying to understand the interaction between heating and cooling processes in this case, in galaxy clusters in a cosmological context, we can start to like reverse engineer and figure out, what might be the relative role of different astrophysical processes. So far, when people think about the formation of non-cool cores, there have been largely two pathways that are considered. So one is the preheating picture, where feedback from active galactic nuclei from very early times in the cluster sort of heats the gas so much early on that it manages to prevent a cool core from ever forming, right? So that's the preheating scenario. So basically you're saying your AGN is just so active and energetic that your core is never super cool. And on the other hand, you have a disruption scenario where, okay, so you end up forming a cool core in clusters, but then a major merger or something else could come in and disrupt the already formed cool core. And now, if you look at these two processes that actually, they are quite different. One is heating from the center, and the other one is things being disrupted by a cosmological phenomenon, so a merger. There is actually an underlying common thread, which is the presence of cold gas. So you want cold gas in order to fuel AGN activity. Essentially, our theoretical models are all converging on the fact that your supermassive black holes preferentially feed off of cold gas. And furthermore, if you have heating in the core, then the cooling rate will decide how much cold gas goes back into the core, right, and manages to sustain the cool core. So with those questions in mind, right, whether we're looking at a preheating versus merger-driven scenario and how these affect the cool and non-cool core states of a cluster as mediated by the cold gas, I turn to the Romulus C cosmological simulation. So Romulus, this is a slide from Michael Tremmel, who is sort of the go-to person. He describes it as certified organic, free-range, locally grown supermassive black holes. What he means by that is that one of the interesting things about the way black holes are treated in Romulus is that they are seeded very early on in low mass halos, unlike a lot of other cosmological simulations where you sort of say, okay, once a halo reaches a certain mass, usually around 10 to the 10 solar masses, you seed a black hole that's like 10 to the 5 solar masses. This means that the black holes are seeded relatively late, right? Because you're waiting for a halo to acquire that mass first. As opposed to here, it's sort of, it depends directly on, do you have some gas that is around 10 to the 4 Kelvin, around the cooling threshold, that meets certain density criteria. It's like low metallicity enough and hasn't formed stars yet, then that becomes a black hole. And so if you look at the formation times of black holes, it's much more evenly spaced out in time than in most of the other cosmological simulations. It is, I can say this for another couple weeks or months, the highest resolution cosmological simulation of a galaxy cluster until TNG 50 comes out. So this actually allows us an effective resolution of 250 parsecs for the gravitational smoothing length, which is quite competitive. And what this means is that by implementing a feedback model that is purely thermal, right? So we're modeling feedback as just an injection of thermal energy into the gas particles surrounding the central black hole. We managed to drive outflows, right? So the gas actually you can see the velocity, the outward movement of the gas, which is very tricky to do if you have coarse resolution, right? Anyone who has worked with cosmological simulations is familiar with how when you dump thermal energy into a coarse gas cell, the heat largely just gets radiated away, right? And so you have to, your feedback essentially has to become extremely bursty, and it's not pretty. So here what we managed to do is, in part because of the resolution, and another part is that we briefly turn off the cooling in the gas particles around the black hole. This is a really, really brief cooling shutoff, I should emphasize, because the gas cell particles around the black hole and the black hole itself are on the maximally refined time step. So the cooling shutoff lasts for only 1,000 to maybe 10,000 years, as opposed to the global time steps, which are 2 to 3 orders of magnitude longer, right? So you have a brief cooling shutoff, and then that allows this self-consistent driving of these outflows. Right, and so another modification that turns out to be important in the way black hole feedback is, AGN activity is implemented, is that the accretion rate onto the black hole is a slightly modified Bondi prescription, and specifically it takes into account not just the bulk velocity of the gas, but around the black hole, but also its angular momentum. And so it sort of takes into account the fact that if gas is rotationally supported, then it wouldn't fall into the black hole. And this manages to tie the activity of the black hole not only to the thermal state of the gas in the core, but also to its kinematics. Okay, right, and then just, as I said, the cooling shutoffs are brief, and the high spatial resolution allow us to drive these outflows on scales of hundreds of parsecs. They actually go out to hundreds of kiloparsecs, even though they're launched locally on scales of hundreds of parsecs. Okay, with that said, again, the power of Romulus is that we really managed to resolve cold gas in these galaxy clusters, right? So when I say cold, in the context of galaxy clusters, I'm talking about gas that is below, for an X-ray community, you could say below 10 to the 6, and that would be fine. But even if I apply a cut of 10 to the 5 Kelvin, right, you can actually see this disk of cold gas at the center of Romulus. And so if you have any sort of questions you want to explore about filaments or cold disks or things like that, then Romulus is really a great resource to work with. So going back to the cluster itself, the way I'm approaching this question is I look at the state of the cluster at a few characteristic epochs, and I've color-coded them as you see over here. They're chosen based on the black hole activity at each of those rates, at each of those times. So basically, the first band, so the gray one over there, is a period of relatively high star formation, and all of these terms are relative, right? Relatively high star formation and relatively low black hole activity when the cluster is still in its isolated state. So that is state 1. State 2, the black hole activity is higher, right? So the dotted line, the dotted blue line is basically averaging the solid blue line over timescales of 1 gigayear because the black hole activity is quite stochastic. But there's an increase in the AGN activity, which corresponds to a quenching of the star formation rate, which you see in the red. That is phase 2. Phase 3 is the star formation is already quite quenched, and just at this time, there is the beginning of a 1:8 mass ratio head-on merger. Okay, so that is phase 3. So this is star formation is quenched, merger is beginning, and then phase 4 in the orange is once, and this is a bit of a spoiler, but the cool core is disrupted and the merger is well underway. Okay, so these are the 4 phases we talk about. Either cluster is isolated, black hole activity is high, is low, cluster is isolated, black hole activity is high, then merger is starting to begin, star formation is quenched, and then the merger is well underway. And this is basically the result that you get in this scenario. So once you plot the entropy of the gas, right, normalized by the value at R500, because this is the sort of same formalism that Mark Voigt and people use in their models, you see that in all the phases before the merger, right? So whether you're looking at the black and gray line or the pink or the purple, the entropy in the core within error bars doesn't really change, right? And it's really once the merger is well underway in the orange band that the core entropy is elevated above all the other values, right? So keep in mind, when you're looking at the purple band, right, that is a period of high AGN activity when the cluster is isolated compared to the black case, right? And even though you have this strong heating source at the very core, you're not seeing an increase in the entropy, right? So how do we explain this, right? Basically, what we're seeing here is that even high levels of AGN activity do not manage to significantly affect the core entropy. So now we can really dig into the particle level data here, right? So what I'm showing here is on the x-axis, you have the cluster-centric distance. On the y-axis, you have the entropy, and both axes are logged. What you see in the white to gray, in the gray scale, is essentially the PDF, right? So it's the log of the number of gas particles at each point in this phase space, right? So basically, if it's darker, that means there's much more gas there. And okay, so that basically shows you the entropy distribution of all the gas in this cluster. In the purple line, you see the mass-weighted average profile of the hot gas. So everything that's hotter than 10 to the 6th Kelvin, this is what you would see with a telescope like Chandra. In red, you see particles that were ever within 1 kiloparsec of the black hole and therefore directly received a thermal energy injection. Okay? And then there's everything else, right? So, so here are the takeaways. Essentially, the first panel corresponds to, low AGN activity, isolated. The second panel, high AGN activity, still isolated. Third panel, the merger has just begun, right? And then the fourth panel, the core is clearly officially categorized as a non-cool core. And so you'll notice that the evolution actually proceeds in sort of 2 steps between the top and bottom. So first of all, in the top 2 panels, when the cluster is isolated, you have an abundance of low entropy gas in the core, right? So essentially of entropies of lower than 1 keV centimeter squared. And this sort of low entropy gas completely disappears at the beginning of the merger, right? So that is step 1. And then step 2, between 11.65 and 12.15 gigayears, is when the mass weighted average entropy of the remaining gas, right, gets increased as well. So it's actually a two-step process. First, you reduce the precipitation rate or the formation rate of low entropy gas in the core, and then secondly, you manage to heat up the gas that the remaining gas that was originally what I guess you would call cool but not cold, and then you manage to elevate it into a pretty warm, hot state. Part of it has to do with the fact that you're increasing the cooling time of the gas, right? So essentially, again, you see that at all the epochs when the cluster was isolated, the cooling time to free fall time ratio within the core was essentially indistinguishable within the core, within error bars. Whereas once you have the merger happening, not only is it systematically higher than all the other earlier epochs, but now there's a systematic increase towards the center, which means that if you have gas that is cooling, let's say at, I don't know, 0.1 R500, right? And it falls in towards the center, it becomes progressively harder and harder for that gas to cool. So part of what's happening in this merger disruption process is that it becomes increasingly harder for gas to cool as it falls towards the center. One of the first things that people talk about as a heating mechanism, both in the case of AGN-driven outflows and in the case of mergers, is the dissipation of turbulent motions, right? And again, so Mark Voigt has recently developed a model where he discusses essentially, how turbulence is effective at heating the gas. And so there's two competing effects here. If the turbulence is too high, right, and essentially he's normalizing this by the circular velocity of the gas at that radius to give you an idea for how strong the gravitational potential is there. If the turbulence is really high, then you just end up heating up the gas, right? And so if the gas is too hot, then precipitation is really difficult. The formation of cool gas is really hard. On the other hand, if the turbulence is too low, then essentially the effect of turbulence motions is negligible compared to the gravitational potential. So you have this some sort of sweet point. And in his very idealized model, this perfect ratio between turbulent and circular velocities for optimal precipitation is at about 0.5, which you will notice in the right-hand plot over here, is barely achieved in our simulation outside of like the central 0.04, 0.03 or 0.04 R500, so just a few, like 10 kiloparsecs or so. And I would take that part, quick point. I wouldn't be too concerned about the fact that you don't reproduce the 0.5 exactly in this model, because it's a cosmological simulation. The Voigt model is completely idealized, but you can still see a qualitative result that if the case were that turbulence was driving the heating motions, then you would expect the ratio of turbulent velocities to circular velocities to be higher in the post-merger scenario than during the isolated epochs. And in fact, the opposite is the case, right? So turbulence is not what is driving this heating. Instead, what's happening is that the gas is being mixed. So the hot and the cold gas in the cluster are being mixed by direct sloshing around of the substructure, right? So this is a model that John Suhon and a lot of other people have seen in idealized simulations of binary cluster mergers. And so this is what I'm trying to show here. So basically, I'll just quickly start with a qualitative picture, right? You just see that at 11 gigayears, so well before the merger officially happens at 11.65, which is where the subhalo is first considered unbound, you already have the subhalo sort of penetrating the core of the cluster, right? And along with it, bringing gas that is sort of warmer. Each of these boxes is 500 kiloparsecs aside. So it actually physically mixes the hot gas from larger radii with the cold gas in the center. And that's how it starts to heat up the gas and reduce the precipitation rates. and then by the time the cool core is completely disrupted at 12.15, well, you see that the gas has been sloshed about the core a few times already, right? So mixing really is what's driving this. You can get a qualitative picture just by looking at these maps. Again, the white particles are gas particles from the subhalo. Everything else is the main halo. And sort of to quantify this a little bit more, right, you can see what I've shown in each of these panels is that for the labeled time period, on the x-axis, I show the entropy of a certain group of gas particles at the starting time, okay? And then on the y-axis, I show where those same particles ended up in the entropy space at a later time. So how has the entropy of these particles evolved over this given time period? And I've done this I've been like quite generous about this. I've selected all of the gas particles within the central 200 kiloparsecs, right? And so essentially, when the cluster is in the isolated state before the merger begins, right? What happens is that the low entropy gas all gets heated up by the AGN, right? And so that's why you essentially see, if there were no evolution, you would see the green line, right? The entropy of all the particles would just remain the same. Instead, in an isolated cluster, the AGN preferentially heats the low entropy gas in the core and increases that value. On the other hand, once the merger starts to happen at 11 gigayears, there's some of the low entropy gas gets heated up, sure, but also some of the gas that was originally high entropy gets pulled down, right? So you see this dramatic increase in the scatter of this histogram. By the time you reach 11.65 gigayears, the AGN activity is order of magnitude lower, and you don't have this heating happening anymore. So it's really just an issue of hot gas from larger radii being brought in and being cooler than before, but still increasing the average entropy within the core. And the cool core is not restored by the end of the simulation, right? Yeah, so that's basically the conclusion. The closing point that I wanted to make is that we can use simulations like Romulus to make predictions for, we can test the observations that we have of Romulus with upcoming telescopes, right? So you can directly measure turbulent velocities in galaxy clusters using something like CHARM, or I guess it's now called XRISM, Athena, or LYNX. And it's very important to note that this is a very qualitative analysis, but it's important to note that the measurements that you would get for the turbulent velocity dispersions are sensitive to the resolution of your instrument, right? If your resolution is relatively low, like in CHARM, you're essentially averaging over a pretty large volume. And so if you have small areas of very high velocity dispersion, but they're surrounded by a lot of gas with low velocity dispersion, you're going to have a systematic underestimate of the amount of turbulence in your medium. So this is the sort of systematic that we can test really well with Romulus and other simulations like this, and that's something that I'm interested in pursuing further. And I would just note, if people are thinking about how to do this with something like LYNX, Romulus is a little bit too cold for just to use the iron complex lines, which are sort of everyone's favorite. But it's still an open question how we can harness cooler lines to measure turbulent velocities in galaxy clusters. So I'll just close off by saying that I looked at Romulus C, which is the highest resolution cosmological cluster simulation to date, to study in detail the heating and cooling processes, the interaction between them, and how they form a non-cool core. And essentially the conclusion that we see is that while AGN activity manages to regulate star formation and gas cooling, it's a system in equilibrium, and it doesn't manage to disrupt a cool core once it's formed. And even though the black hole is seeded much earlier than in most other cosmological simulations to date. And instead, it is this relatively major, very low impact parameter, so head-on merger, that manages to disrupt the core. It is not through turbulent heating, which is often suggested as a key heating channel. Instead, the heating comes mostly from mixing, so direct sloshing of gas between different radii by the substructure. And the observability of turbulence will depend on the spatial resolution of the instrument that you're using, and this is something that this is a systematic that you can study pretty well using simulations and synthetic observations. Thank you. Great.
Really great work. Two questions. One is, can we borrow your links figure?
My what?
Can we borrow your links figure?
Yes.
And also, the color scale on that, I'm guessing, was in turbulent velocity width in kilometers per second?
That's correct.
Okay. And then the second question was, in the plot of accretion rate and star formation rate over time in Romulus C,
Yeah.
the black hole looks bursty on the order of a Dickey-year time scale, which is fine. I'm just wondering, like, how coupled is either the period or the amplitude of the burstiness to that by hand cooling pause that you add? For example, 10,000 year one versus 100,000 year one. In other words, is it a really sensitive knob that you can use to tweak the burstiness?
Okay, that's a great question. My understanding is, so the cooling shutoffs are of the order of 1,000 to 10,000 years. The burstiness that you observe is on scales of like 0.1 gigayears. So it's very unlikely that those two things are correlated. Yeah, and essentially you do see the outflows happening in a pretty the outflows aren't like they don't happen essentially immediately after a feedback event. Is not if you look in detail at just how the gas is moving, it's not a brief episode immediately after a feedback event. It's more prolonged. So yeah, basically I think no.
Is that bursting real, or is that an artifact of your model?
I would say the burstiness is real. So it has to do with how much low temperature and low angular momentum gas is present in the core, right? So it's actually a self-consistent prediction, and that does indeed go in cycles. So if you were to look at something like this, right, essentially it's mostly gas that is. You'll notice that at r equals 0, right, you see a few red points sort of lining up along the y-axis. Those are the gas particles that end up directly getting heated by the AGN, and you'll notice that they are all preferentially low entropy particles, right? So you really want this low entropy gas with low angular momentum at the core, and this does indeed go in cycles. If you have a bursty AGN event, then you actually have way less of that gas in the core. So I think the burstiness is real because it's a self-regulating feedback mechanism.
Other questions? Let's thank Mila again.
Hi,
Martin.
Martin.
Yes,
So
yes.
sorry.
Don't worry. All the red dots there, they're clearly pushed out and there's a gap.
Yes.
Is this outflow of yours that you were showing early on?
Thank you, Saku.
Oh yes, good call. Of course, that's why I'm here.
Thank you. I had a bit of a brain freeze towards the end, but
No, not noticeable.
oh, great. So the gap in between. Okay, so it indeed has to do with the fact that the gas particles quickly move out to larger radii.
Yes, this is a log axis.
Exactly.
And then, yeah, okay, so it tells you it's bursty as well, because otherwise it would be a continuous thing.
That's true. This is a bit of an underestimate of all the gases that ever get heated just because we don't save all of the snapshots. So it is possible that you have some particles in intermediate time steps that were heated, you know. But, yeah.
Maybe we should have a meeting on rain in astrophysics.
I would love that.
Why don't we organise it?
Actually, my paper is called Rain on the Galactic Fountain. So
Mine's just called quasar rain.
we
And
should.
it's very simple-minded, so it's just time scales.
That's great. I'll take a look at it.
Please,
Yeah.
yes. I'm not going to work any more on it, so if you see a way you can say, oh, I could do that,
Yeah.
then please do.
Okay.
Just let me know, it would be nice to know.
Yeah.
Sounds like Alex.
We haven't done it yet. I am wondering, but we will intend to do it. I don't think so, yes. Yeah, you must have done it. Remind me what I'm supposed to do. I sent it to you. Okay, all right, then I will look for it and I'll send it on.
How long have you been here?
3 months now?
3 months, good. No, not embarrassed not to have noticed. Often the people have been here 3 years and I haven't.
Oh, yeah.
But that means you're going to be with us for a while.
I am, yeah. So I'll be here
What sort of
until I
postdoc do you
finish
have?
my PhD. I'm a pre-doc. So we actually met at the pre-doc journal club.
Yes.
I love donuts, but I need to find the vegan ones because I'm allergic to them.
Very reasonable.
But thankfully they exist in Boston.
I don't think they exist in Dunkin' Donuts, though.
No, but Union Square donuts.
Oh, I've heard about it, yes.
I live right next to them.
Oh, and yet you're still quite thin. You're hardly spherical at all.
Thankfully, I like to do other things to balance the donuts.
Top act. So, yes, that's right. I asked you, why would you be here from Yale? So what is the reason? Oh, money.
No, the primary reason is that I'm a foreigner and rarely offered fellowships.
That's right. So
eligible for
the
it.
fellowship is the money. That's what I mean.
Sure, I would have gotten the funding anyway. I sort of just wanted it more to show myself that I took this attempt.
First combination with quant data for the large scale.
US national like me obviously came later.
Published
I won't tell them. I'm an engineer master.
Okay, that's a subtle way of doing it. You're not wrong to do that.
No, I grew up mostly in Russia, but which doesn't help.
And you don't want a Russian passport?
Oh, I would love. Well, right now I don't know if I would. But it's like,
I usually say get as many as you can.
Russia, unfortunately, at least when I was looking for school, they didn't give out unless you were Russian by birth. So they've changed that since then. But yeah, it's just not. My dad has lived between USSR and Russia for 30 years. Wow. But he got a scholarship to study in USSR.
Way back, they did that.
Yeah, and so he liked it. So then afterwards he just started his own business there.
Very strange. Okay.
Yeah, he was like in that niche of people for whom it worked out really well because he was a scholar in